So this video is on capacitors in series and in parallel, and it covers what's in chapter 27-4. Okay, so in series, so when you have a circuit, when you have things in series, that means they're one after the other. So here's a circuit diagram on the right. So we've got our single cell battery, some wires, and then we've got capacitor 1, capacitor 2, capacitor 3, and they're all one right after each other, so they're said to be attached in series. Okay, so since no charge can actually flow across the insulator of your capacitor, that means that since charge must be conserved, right? So if you imagine, so let's pretend that it's the positive charges coming out of the battery. Positive charges will build up on this very top plate of capacitor 1, which will push the positive charges away from the other plate, which will build up on the top plate of capacitor 2, which builds up a potential difference and pushes the positives away, and again, all the way around. But since charge is conserved, that means each capacitor has to have the same charge. So, since the charge is the same on all of them, and then you also know in series that the sum of the potential differences across all of the capacitors must equal the terminal voltage of the battery. So that's really just a statement about conservation of energy, right? So the battery, you're gaining some potential or gaining energy from the battery, and then you're losing energy across each of the capacitors, and the gains have to equal the losses. Now in parallel, so in parallel means that one side of all the elements is connected together and the other side is also connected together. So if you look at the circuit diagram at the bottom here, so one side of these two capacitors are attached to the negative terminal of the battery, the other two sides to the positive terminal. So they're said to be connected in parallel. Well, and when you have things in parallel, the potential difference across each must match the terminal voltage of the capacitor. And really, effectively, you're just making a larger capacitor. All right, so now that we know how to attach things in series and in parallel, so now we can actually define something called equivalent capacitance. So if you have capacitors in series or parallel, you can treat them as a single capacitor with an equivalent capacitance, C equivalent. So, and there's a couple of rules here. I'm not going to go through the full derivation, but it just follows from how things in series and things in parallel work. So if you have capacitors in series, the reciprocal of your equivalent capacitance is equal to the sum of the reciprocals of the individual capacitances. So 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3 and so on for however many capacitors you have in series. And a good rule of thumb to remember is that equivalent capacitance for capacitors in series is smaller than the individual capacitance. Now in parallel it works a little bit different. It's just the simple sum. So the equivalent capacitance is just the sum of the individual capacitances. So C1 plus C2 plus C3 for however many capacitors you have in parallel. So, and then for parallel capacitors, the equivalent capacitance is larger than the individual capacitances. So now you can actually, if you know those rules, you can go through and actually analyze more complicated circuits. So if you have things that are a combination of capacitors in series and in parallel, you kind of break it into bits and go step by step. So we'll see some examples of this in class, but if you look at this diagram at the bottom here, if we wanted to find the equivalent capacitance between point A and B in this little part of the circuit, well, if you look here on the far right, we've got 3 capacitors in series. So we know if we have capacitors in series, well, the reciprocal of the equivalent capacitance is the sum of the reciprocals of the individual capacitances. So we could replace these 3 with a single equivalent capacitance. So if we replace those 3 with a single capacitor, well then on the far right we've got 2 capacitors in series. So in series we just add to get the equivalent capacitance, and we place those 2 in parallel with a single one. And then we would have 3 capacitors in series again, and we can use the series rule. So in general, for any complicated combination of capacitors in series and parallel, you just break it up into individual parts that are either in series or in parallel.